Okay, so more applications of DEs, and these are just so critical. I'm just showing you a bunch of these. I consider it that important. What this one is on is Newton's law of cooling. Newton's law of cooling. And what this states is that if you have some object in a room, and let's say that the temperature of this object is T, capital T, and let's say it's in a room, and this room is temperature TS. In other words, the surrounding temperature, the temperature of this room is TS. So you can think of a really hot object like, let's say, I don't know, a cup of coffee. A cup of coffee in a room, in a cold room or something like that. It's going to cool down that cup of coffee, and what Newton's law of cooling says is that that will cool down proportionally to the difference between these two temperatures. In other words, if there's a massive difference between this temperature and this temperature, it'll cool down much faster than if there's only a small difference between these. And you can think this was 100 degrees and the surrounding temperature was negative 100 degrees, that would cool down very quickly. But if this was 21 degrees and the surrounding temperature was 18 degrees, it cools down very slowly. And so what it says is that the change in temperature with respect to time, little t for time, big T for temperature, is equal to some proportional, so K, times the difference between the temperature of the item minus the surrounding temperature. And that's Newton's law of cooling. Now, so let me just say that again. It's proportional to, so K, the difference between those. Now, if it's cooling, what's happening is that the temperature is becoming less and less. And so what we can say is that negative K, if we're talking about K being greater than 0. Okay, so that's for cooling, because we want a negative change in temperature. It's cooling down. If it's heating up, what it is dt is equal to Kt minus Ts. Okay, if it's heating up, then we want a positive K there. Okay, it's increasing for K greater than 0. Okay, so just make sure, so this is heating here. It applies, I didn't say this, but it applies to heating too. If you place an ice block in the middle of the room, in the middle of a 40-degree room, then that ice block will heat up. Okay, so it applies to, even though it's Newton's law of cooling, it applies to heating as well. Okay, I'm going to go straight into an example of this, and again, really important. Okay, let's do that cup of coffee. Cup of coffee initially at 90 degrees Celsius is placed in a 20 degree Celsius room. Okay, it's placed in a 20 Celsius room. After, let's say, 5 minutes, the coffee is, it's going to work out nice. I won't try and make it nice, but if I come undone, don't mind me. Now let's just say that it drops 50 degrees Celsius. Okay. Find a model equation that predicts poorly worded, but find a model that predicts, find a solution to this differential equation. That's what we're after. Okay, so what have we got? We've got Newton's law of cooling. The change of temperature with respect to time will be equal to K, and the difference of the temperature of the coffee minus the temperature of the surrounding. It's in a 20-degree room, so it will be minus 20. And what it's doing is cooling down, so it's going to be negative K. And what we've got K is equal to R, and it's a positive value. Okay, K is positive because we want this to be decreasing. We've got negative K there as well. Okay, so let's solve this guy. So we should have lots of practice with this. Again, we've got f, we've got dy dx equals d function of y. So what we need to do, flip it upside down and solve for t. So t is equal to the integral of 1 over negative k t minus 20 dt. Now don't get confused between the little t's and big T's. Okay, good. Take the negative 1k out the front, and we just want to do the integral of 1 over t minus 20, which is log e modulus t minus 20. Nothing in front of t, so you don't have to put anything else there, plus c. Fantastic. Good. So there's our little t. So time is equal to that function of temperature. Now, can we get rid of this modulus? Always got to think about that, whether you can get rid of that. Is t minus 20, is that always going to be positive? Now, if you think about the temperature of the coffee, will that ever drop below 20? Well, no, it won't. It's actually physically impossible for that coffee to drop below the temperature of the room. It can't have less energy. So that is actually always positive. Okay, so I'm just going to try to rewrite that here. 1 over k, negative 1 over k, log e t minus 20 plus c. Okay, that's perfectly acceptable. That coffee cannot become under 20, so this cannot actually be negative. So we can comfortably do that. Okay, now let's rearrange this guy. Or should we put our initial values in? Again, we're going to get initial values, so it's better to just actually rearrange this. So therefore, what have we got? T minus c. So we have, so write it in little letters because you know it's going to be a e to the power of. T minus c, we're going to times it by negative k, so it'll be negative k times all that, and then we're going to raise it to the power of e, and that's equal to t minus 20. So therefore, t is equal to 20 plus e to the negative kt minus kc. And what that is equal to is that's 20 plus a e to the negative kt. And if I had more space, I would write where a is equal to e to the negative kc. But a lot of people don't do that. Please do that. I'm going to run out of space if I don't do that. So sorry about that. I would write where a, capital A, is equal to e to the negative kc, this part here. I'll put that down. Okay, so there's my t. That's t there. Okay, my capital temperature. Now we just got to find our constants a and k. So let's substitute in. Firstly, do your initial condition. Initially at 90 degrees, so when time is equal to 0, temperature is equal to 90. So 90, I'm doing different colours. Mix it up. 90 equals 20 plus a, e. At time 0, that's just going to be 0 up there. E to the 0 is 1, so therefore a is equal to 70. This gives us our new temperature, equals 20 plus 70 e to the negative kt. And so now we've only got 1 left to do. Let's find k. Let's substitute in. I'll just change colours. Substitute in. Green's not a very good colour. Pink. So therefore substitute in. Next one, after 5 minutes, so when time's equal to 5, it's 50 degrees. So 50 equals 20 plus 70 e to the negative k when time's equal to 5, so negative 5k. Let's just quickly solve this. 20 goes over to that, it's 30. Divide by 70, so you've got 3/7. Oh, I picked horrible numbers. I was hoping it was going to come out nice. Just let me check that. 30 over 70. 3/7 equals e to the negative 5k. So therefore, k equals the log e of 3/7 divided by negative 5. So negative 1/5 log e 3/7. Yuck. Let's plug this all in now. So our temperature will be equal to, I'll change colour, go back to red because we're about to write our solution. So temperature equals 20 plus 70 e to the negative k, so it will be positive 1/5 log E 3/7, that's K, T. Okay. Again, let's put this log E part down into here, just like we did last time. So that's 20, I'm going to run out of space, plus 70, and in brackets I'm going to have E to the power log E 3/7 to the T over 5, which is equal to 20 plus 70, and this is all equal to 3/7, so times 3/7 to the power T over 5, and there we go, there's your temperature. That's what temperature equals, and there is your solution to that. So this tells you that after a certain amount of T minutes, your temperature will be equal to 20 plus 70, 3/7 T over 5, and that's your model. So the key parts here are to be careful with your constants, be careful with modulus, and get used to this sort of way of working out different constants. And you can see it ends up not being logs or e's or anything like that, it just ends up being powers. Okay, so there's an example of Newton's law of cooling.